Hello everyone, I'm Donal Murphy, Marketing Manager for NVIDIA's GPU Technology Conference, otherwise known as GTC, and I want to welcome everyone to GTC Express. GTC Express is a year-round extension of the great content available at GTC, providing insight and unique perspectives on GPU computing and GPU technologies from top scientists, researchers, developers, and industry practitioners. If you're new to GTC Express, welcome, and I encourage you to come back often and participate. It's my pleasure today to introduce my colleague Jeff Kiel, Manager of Graphics Tools at NVIDIA, who will be presenting on the topic of Learn How to Profile OpenGL 4.2 with NVIDIA Nsight Visual Studio Edition 3.1. He'll be assisted by our other colleague Daniel Price, who's a programmer in the graphics tool department at NVIDIA. And Daniel will be helping with the Q&A, so you're welcome to submit your questions at any point during the presentation by typing them in the area provided on your screen, and Daniel will address them in real time. Daniel and Jeff will also have a live vocal Q&A at the very end of the presentation, so you can submit your questions again at any point during the entire presentation and Q&A. We will be making a recording of this webinar available for download on the GTC website in the next few days. So with that, welcome Jeff.
All right, thanks very much, Donal. I appreciate very much your introduction. And thanks everybody for joining us today. Hopefully you will leave today's presentation, today's webinar, with a deeper understanding of how you can use Nsight Visual Studio Edition to do performance tuning on either your OpenGL. We're going to be specifically focusing on OpenGL content, but also as well as on your D3D content. We're really going to talk about a number of different areas today. The application we're going to be using is an application that was developed internally on our tools team, and it's called Bindless G-buffer. It uses a new feature of OpenGL called Bindless Graphics and Bindless Texture, which basically allows you to use effectively GPU side pointers from within your shader programs. And I'll get into that more deeply as I explain the application a little bit more. And basically what we're going to do is we're going to use Nsight to do a performance tuning run on that application. So we're going to start from literally the original version that was written by the engineer that was doing this, and then kind of walk through a couple of different scenarios on how he was able to improve the performance of the application, both on the CPU side using more of our application tracing, and then as well on the GPU performance using our frame profiler. And also, as noted there, we are going to demonstrate how to use the NVTX or NVTools extension API to add some annotations to your code, which aren't necessary in order to use Nsight, but are helpful if you do decide to use them, because they can help you to get more context in terms of what's happening in your application, and you can see that in a number of different screens as we go through things in Nsight. So before we get started on the demo, I wanted to give you a quick overview of what Bindless G-buffer is. So Bindless G-buffer is basically utilizing this bindless graphics capability in order to create a deferred renderer. Typically, deferred renderers in the past have usually used multiple output targets, multiple render targets, and you would do kind of what you see here. You've got a normal map being put out, then maybe you've got a shininess map, you've got a diffuse map, and so you would basically have multiple different render targets, and you could run a pass that would basically populate all these different render targets with all the different data. Then on the back end, what you would do is you would consume all those render targets and do all of your lighting and all that. And so that's really helpful. But if you think about it from a classic CPU programming perspective, it's kind of odd to write everything out to separate locations and then pull them back together. Typically what you want to do is you just want to make a structure and put all those values in a structure and be able to read those out for every single fragment. So it kind of turns things on its ear, kind of the structure of arrays versus array of structures concept. Turns things on its ear and really enables things to be a lot quicker when running on the GPU, and things make a lot more sense. And really the entire application is kind of broken up into three phases. The first phase is our generate phase. The generate phase is where we are going to go through and we're going to render all of the geometry and collect all of the information that we need for our deferred render. So again, our normals, our texture coordinates, and all that. And we're going to do that for every single fragment in the scene. Then you're going to go through your sort phase, where we're going to take all the fragments that we've collected for each pixel in the eventual render target, and we're going to sort those to make sure that we are definitely going to be rendering from front to back. And the idea there, obviously, is that this allows us to do order independent transparency. So that kind of comes for free in this algorithm. It doesn't really matter what order I submit all of my geometry in; they're going to be sorted anyway, and so we can take care of that later. And then finally, we'll go through our shade phase. So we're going to go through each one of those fragments, and I'll go in a little bit more depth in these next few slides. So the first phase, basically what you want to do, what you're going to look at is you can kind of consider this blue square right here to be effectively a render target. And for each one of the pixels on the render targets, we're going to create a structure, as I was saying earlier, that is going to give us all of our information that typically you would put into separate render targets. Now we're going to put it all into just a structure. And it's basically a linked list of fragments per coordinate on the eventual render target. And we're going to say things like our eye position, the alpha color, the eye normal, material index, and any UV. And the way you want to think of it is some of these are going to happen on the GPU and some of these are going to happen on the CPU, but we're going to submit a bunch of draw calls, and those draw calls are going to be split up into primitives. This is going to be happening on the GPU, so this is kind of virtual code, if you will. Each one of those primitives are going to be rasterized, and so we're going to have effectively a loop across every fragment. And we're going to basically do three things in the generate phase. We're going to allocate a buffer node out of a heap that we create, and that's one of those bindless buffers that we're going to have. We're going to populate that. We're going to fill in all the information in this guy, and then we're going to insert it into a linked list of nodes for this individual pixel. And again, that's going to take advantage of our next pointer here. Our next phase is going to be our sort. The sort is very simple. We're actually going to submit just one piece of geometry, and that's effectively going to give us a thread for every pixel on the screen. And that's going to give us, again, that the rasterizer is going to create a thread for every pixel, and we're just going to do a simple selection sort. So all we're going to do is we're going to render, or we're going to go down that linked list multiple times, each time bringing up the smallest item, or the one that's closest to the camera. And so it's real simple. We just go ahead and figure out which one's closest to the camera, bring that to the beginning of the list, and then keep on going until you're done at the end of the list. So it's a nice simple selection sort. It turns out that given the number of elements we have in the list, which is going to be, on a maximum probably about 10 or 12, selection sort actually works pretty well. The next phase is our shading phase. And again, this is going to be very similar to our sorting phase, where we're going to submit one full screen quad, and that's going to allow the rasterizer to create a bunch of fragments and effectively create a bunch of threads that we can run our algorithm on. And we're going to initialize our color to 0. Then what we're going to do is we're going to take the head pointer for our G-buffer nodes, and for every one of those, we're going to kind of do just a simple traversal down a linked list. We're going to figure out what the alpha component is for this individual fragment. That's basically based on the amount of alpha that we currently have accumulated. We're going to do a simple Phong lighting model, and you can do that with as many lights as you want. It's one of the powerful things about using deferred lighting. You can put lots and lots of lights in there, and they're much cheaper than if you have to do multiple pass lighting. We're going to figure out what the node color is, and then we're just going to simply accumulate that color and then subtract out the alpha for that individual fragment. Once we're done with that, then we're going to go ahead and sum in the remainder. For the remainder of the alpha, we're going to sum in the clear color, and that takes care of any buckets that might have no fragments in them, for instance. All right, so without further ado, we'll go ahead and start up Visual Studio and show you guys how things work. So the first thing we're going to do, as I said earlier, hold on one second, sorry. Looks like I already had that open. Not sure why I did that, but okay. So the first thing we're going to want to do is, oh, that's why. Sorry about that. Now I see where it was. I already had it open. The first thing we want to do is we're going to decorate our code with these NVTools extension annotations. First thing I want to do is go through and kind of give you an idea of what is available in NVTools extension. Now this is a library that we provide. It actually ships with Nsight Visual Studio Edition as well as the CUDA toolkit. With the CUDA toolkit, it ships with support for Windows and Linux and Mac, so it's actually supported on all three platforms if you get it via the CUDA toolkit. Because Nsight only supports Windows, we only support the Windows version Windows version of NV Toolkit when you get it via Nsight. But there's a number of different things that you can do with this. There's a number of different ranges that you can do. So the first thing you can do is you can fire off kind of a one-off event, and this is this NVTX Mark or Mark EX version. The idea here is that this is going to be a single happening. So you can imagine maybe you're changing your level, and so you want to fire off an event that says, okay, I've got a new level starting. Or maybe you're getting a certain network packet, and you wanted to denote that in your trace or in your application. So those are for kind of the single fire and forget events. And again, a couple of examples of how you might want to use those. The next one is a couple of different ranges. The first one is the range start stop, and then the next one is the range push pop. And you can see here I got the push version right there, and the pop version is right below. The difference between these two is the range start stop actually allows them to overlap, so I can actually have start and stop ranges overlapping, and this is really useful if you're starting the range in one thread, for instance, and maybe ending it in another. And so that'd be a really useful thing, so that you can say, I just want to say, you know, maybe you want to denote when you receive a certain message or you start a certain job, and maybe that job is actually completed on another thread, or the message is maybe processed on another thread. So you can start the range on one thread and end it on another thread. And again, it doesn't matter. These are not going to support nesting or anything like that. They're just going to be discrete ranges. So those could be helpful. The next one is the range push pop. And this is going to be stuff that happens on a single thread, and this is going to be the one that we actually use when we annotate our code. And this is useful for instance, if you're doing a graphics application and you have things that are a little bit more frame based, then you can have a push pop range for the entire frame, then maybe a push pop range for different aspects of your rendering. Maybe you've got you know, a diffuse pass and a lighting pass, or maybe we've got a deferred pass and a resolution pass, and then maybe some full screen effects that you do at the end. You know, however you have things set up. And then even you can go deep as you want. So even within a certain pass, like maybe a Z-buffer pass, you want to talk about when you render your static objects versus your dynamic objects and things like that. So you can kind of put these as deep as you want to, again, give you as much context as you can have when you're looking at things, both in the analysis and in the frame debugger and frame profiler inside of Nsight. And again, these are all available with both Nsight and the CUDA Tools Edition, supported on multiple platforms as well. I do want to note that we are looking to support some of the new capabilities that are in OpenGL 4.3, including the KHR debug or the ARB debug output extensions. We don't have those yet, but they are in the pipeline to be done. You can probably look for those sometime early next year to be completed. And basically, they will function exactly as the same as you have for the NVTools extension capabilities, and all the same places that you'll see us use the NVTools extension during our demo. You'll be able to see those same things for the KHR debug and ARB debug output. All right, so now what I'm going to do is I'm going to go ahead and go into my renderer function. I'm going to find the call that actually does my rendering, and now I'm going to go ahead and add those annotations. And I want to do this just to show you how simple it is to do it. So basically, I'm just going to say NVTools extension push range push, and I'm going to use the ASCII version, and I'm just going to call this the frame. And as you can imagine at the bottom, I'm going to go down to the bottom, I'm going to say NVTools extension range pop, and that one doesn't actually take a label. Now remember, there's a couple of different versions of these. I'll bring that back up. There's both the regular one, the one that we're using today, but there's also the push EX one. The reason why you want to use the push EX one is because you may want to use that one, is that it actually allows you to do a few more features, in that you can specify things like a different color for each one. You can give it just different attributes. You can see right here, I can have a version on this, I can have a size, I can specify, you know, a user specified category, I can tell what type of color type it is and do a color. So there's even more information you can put in here. We're going to use the very simple version for here, and so everything's going to turn up as a single color. But if you wanted to do it a little bit more fancy, you can do that with that. All right, so now what I'm going to do is I'm going to use our friend copy paste, and I'm going to go ahead and paste a few of these right before each one of these different phases that we were talking about. Again, this is our generation phase, and then we also have our sorting phase and our rendering phase or shading phase. And I'm going to go ahead and include the memory barrier as well. The reason why I want to do this is first of all, effectively the cost of the if I can type and speak at the same time. The cost of the rendering, you can imagine that you're going to want to have the entire rendering all in one bucket, so that when I do things like look at it in the frame profiler and see how much it costs and things like that, it's a little bit easier to see. And basically what these memory barriers are for is that it helps me make sure that that individual portion of the rendering is finished before I move on to the next. And as you can imagine, you don't want to have, it's basically a threading problem. You don't want to have a bunch of threads that are trying to access those linked lists and write to them potentially, while I have another bunch of threads that want to come in and try and read from them. So that's why you need to put those memory barriers in there to make sure that I'm finished with my generation phase before I move on to my sort phase, and finished with my sort phase before I move on to the shading phase. So now we're going to say sort G-buffer. Golly, I really cannot type. And then finally we're going to use our shade G-buffer. All right. So then I will go ahead and compile that. Compiles usually pretty quickly. And then I want to show you just really briefly what those will show up like. And again, I'm going to show it even more in depth as we go. But so I'm going to come up to my Nsight menu, and then I'm going to say Start Graphics Debugging. Note that I also have a little toolbar icon here. I'll probably use that for the rest of the demo, but this one I'll go ahead and use the menu. So I'm going to start Graphics Debugging. I'm going to go ahead and hit Control Z in order to bring up our hotkey and activate our HUD. And then I'm going to hit the space bar in order to pause my application. And now I'm going to switch over to Visual Studio. Oh, did I? All right, looks like I might have missed a pop. Let's go check that. Ah, I did. See? That's why you don't. All right, let's see. Sharp eyes, there we go. All right, that should fix it. All right, we'll try that again. All right, so again, I'll hit Control Z to activate my HUD, hit spacebar in order to pause the frame. There we go. And you can see here I've got my frame denoted here, and then I've got my G-buffer. And I'm going to zoom in over here because it's a little bit hard to see because they're so short. But I've got my G-buffer, then my sort, and then my shade pass. So you can see here already that in my scrubber, where I can sit here and I can scrub through my frame and look at where my different calls are, this is already very, very useful to be able to go, draw a call at a time through my entire scene. So you can see that there, and again, we're going to talk about it more. The other thing I'd like for you to note here is, note how we actually do this scene. As I scrub through it, you can see that, although it's hard to see, you can kind of see behind, you can see that each draw call is coming in one at a time. You can see them kind of highlighted in the back. Let me actually move off of there. There you go. You can see those highlighted in the back. So basically what we're doing is we're doing each draw call one at a time, and we've got a whole bunch of boxes basically that we're going to be rendering in the background. That's going to be important as we go through our new scenarios in terms of looking for where our performance is costing us both on the CPU and on the GPU. And you can see also that as I scrub on the target, you can see that it's scrubbing on the host as well. All right. Let's go ahead and exit that and give you a quick synopsis of what we did in this first scenario. So in the first scenario, what we did was we kind of explained how things work with NVTools extension. Then I went ahead and added some of those annotations into my code, and then we showed you in the frame debugger how you're able to use those annotations in order to figure out where I am in the scene and figure out, for each draw call, which phase am I in my renderer. All right, let's go on to our next scenario. So in our next scenario, what we're going to do is we're going to try and start to figure out where am I spending all of my performance. And when you're trying to figure out where your performance is being spent, the first thing you want to do is determine whether I'm more CPU bound or I'm more GPU bound. Now there's a couple of different ways to do this. One is by using all of our performance graphs that we have, and I'll show you those in just a minute. But the other one is to use our analysis capabilities, and that's what I'm going to do first. So I'm going to come up here to the Nsight menu and then say Start Performance Analysis. And this is going to open up for me a window that will give me the ability to set up all of my performance analysis parameters. Now, one of the things is that this goes ahead and gives you all of the parameters as you had them in your solution in Visual Studio. Note that you don't have to have a solution in Visual Studio in order to use Nsight. What you can do is you can create a dummy solution and just basically have it be a dummy Win32 application, and then Nsight hangs all of its parameters off of the solution. And so you can just simply come in here and point it to, when you're using the frame debugger, you can point it to where your application resides, what your command line arguments might be, and what your working directory might be. So that's really powerful if you happen to be using CMake or maybe some other type of make capability and you don't actually use projects. That doesn't mean that you can't still use Nsight either in the frame debugger as we have this set up here, but also as well in the analysis section as well. All right, so let's go through a few of the setup capabilities that we have here. The first thing we have is the ability to specify how we want to start and stop our data collection. I'm actually going to start that manually. The reason why is I don't want to be charged time for all of the initialization. I really only want to do a sampling of when my rendering is happening, and so it's really helpful to be able to just simply start it manually. Once the rendering starts, you start it and then save off your data. The next thing we're going to do is show you a couple of different activity types. You can either trace just this individual application, or you can trace the entire process tree. This can be useful if you have an executable that maybe fires off other executables to do some work. Like maybe you do some compilation of code, some of your shader compilation. Maybe you're doing that in a separate executable. So you can make sure that you capture that if it's germane to what you're doing in your analysis session. Make sure that you capture that along the way, and you can take that into account when you're trying to figure out where your performance issues might be. Then also, if you're a CUDA developer, you can profile a CUDA application, or again, you can do the entire process tree on the CUDA side. But again, we're graphics, so we're going to go ahead and just trace the application. Then there's three things I'm going to trace here. I'm going to trace the system, which is going to give me all of the CPU tracing as well as the module tracing. I'm going to trace the tools extension, which again is that NVTX that we decorated our code with. And then I'm also going to trace OpenGL. Sounds like we've got a little bit of noise on the line. Hopefully that'll clear up shortly. And then I'm going to come down here and just simply launch my application. My application will start up. You see it's running right there. And so now I'm just going to say start. I'm going to count to 3. You know, you don't want to collect for too long because it can take quite a lot of data. It can generate a lot of data. So I'll stop there. And now it's going to load up all of that data that we've collected inside of our analysis tool. And again, I encourage folks to mute their lines if they could. It sounds like we still have a little bit of noise on the line. All right, so the first thing that... Go ahead, sorry. Okay, everyone can hear me now again? Great. Okay, so the first thing you'll notice is once we finish up, we come in with our summary screen. And this is really great because it gives you all the information about the session that you ran, because these are files that are saved off into your documents directory. And so you can come back to these and revisit them as you see fit, or you can share them with other people. And this is great because it gives you what the working directory was, what the application that you ran was, so that you can keep track of maybe what version that you were running. And then for each one of the domains that you're tracing, it'll give you a summary of that domain. So in this case, we were tracing OpenGL. So it shows me that we were about 15% busy on my CPU cores, and then our GPU is about 15% busy. So that's pretty low. It looks like we're not really doing a whole lot of work there on the GPU. The GPU is starving a whole lot. So we can dive in a little bit more and even show that even further. Next thing I want to do is show the timeline. And this is where those NVTools extension markers are going to come in really, really handy, so that we can figure out where our frames were within the trace. So you can see right here I've got a whole bunch. This is probably that last one as we were just exiting. Now what I'm going to do is I'm going to use the Shift key and the left mouse button key, and I'm just going to highlight a small area that allows me to zoom in and see a bunch of frames. And you can see there I've got, you know, maybe 20 frames. I'm going to zoom in just a little bit further, maybe zoom in on just about 4 frames. And again, I'm using that Shift and left mouse button key. Note also that you can use the mouse wheel. If you have a mouse wheel on your mouse, that will move the entire screen up and down. But then if I use the control mouse wheel, that will also allow me to zoom in and out on my trace. So those are really helpful. All right. Another thing you'll notice is that we've got a lot of information here that's maybe not interesting. Like we've got some threads here that have 0%. We've got a whole lot of great filtering capabilities inside the analysis. These are kind of high-level filters, so I could look at just things on the system, just things in graphics, or just things on compute. I'm interested actually in all 3 of those, so I'm going to leave those up for right now. But I can come in here and do even finer grain filtering. So I can say something like, I'm going to say only give me threads whose core percentage are greater than or equal to maybe 2%. And that's going to eliminate any threads that are really not that interesting in terms of what we're doing with our tracing. So that can be really helpful and really useful. All right. I'm going to move this a little bit out of the way. First thing I want to do is look at our system overview. The system overview is very powerful because it gives you a cross-section of what's happening on all of your CPU cores, and it gives you an idea of when your application was active. That's going to be these green bars that you see, or these green mountains, and then you can also see when maybe other processes were active. And you can see here that across the cores, we're not really taxing them too terribly much. It looks like we kind of migrate from one core to another, and we're always a little bit busy, but we're kind of migrating from one to another. Then down here, we can actually see for each process. I'm going to zoom in on this again using that shift and left mouse button, because this is powerful to help you to see what other processes we're running. This is some maybe communication. This is maybe some of our software for GoToMeeting. This is my audio recorder. And what is this one? This is just the system was coming in. This is really powerful because you may actually see hitches in your application, but they may not be due to something that you were doing in your application. It may be that some other process is waking up and stealing some of your CPU cycles, and that may be causing what your performance problem is. So this is really helpful to be able to see, okay, here's a process that went really high, and it looks like that was this audio recording capability. So you can look for those and make sure that it's not necessarily a problem with some other process that's stealing some of your cycles. All right, I'm going to go ahead and use this one to get rid of that. Now I'm going to drill in on our OpenGL because we're really going to focus in on what's happening on the GPU. And you can see here, actually let's leave those in because I think our NVTools extensions are in there. But I'll go ahead and zoom in on maybe just 3 frames here. And you can see here that our CPU and our GPU are pretty close in terms of when the frames are rendering. So right here on this brown bar, this is basically marking, and these are all clocks that are aligned to each other. And so I can see here that on my CPU, this was frame 2428, and on my GPU, this is 2428. So it looks like my CPU and my GPU are skewed just a little bit. There's a little bit of lag there, but in general, that's not a whole lot. That means that our CPU and GPU are fairly lockstep in terms of the performance. Then the other thing you want to look at is when you look at one GPU frame, you can see here that I've got a whole lot of time that I spent waiting, and then all of a sudden it submitted a whole lot of work, a whole bunch of draw calls, and then a couple of more calls there. And let's actually drill a little bit more deeply in here. You can see here, this is all of those quads or all those boxes that we were drawing. And the great thing here is you can see the incredible amount of parallelism. I probably won't even be able to zoom in as deeply as I want to. The incredible amount of parallelism you have on the GPU in terms of the number of active calls that you can have. And so you can see I've got, who knows, 50, 30, at least 40 different API calls, different draw calls that are active at any given time. And then you can see here over at the end, these are the last 2 calls. So this is going to be all of our rendering phase, and then this is going to be my my submission when I did my sorting phase, and then the last one here is going to be, actually let's zoom out a little bit, make it a little bit easier, and the last one here is going to be my shading phase. So you can see this is all of my rendering. It happens kind of all up front, and then these 2 kernels execute in order to do my shading, my sorting and my shading. So what I can tell from looking at this already is I'm obviously CPU bound, and the biggest thing is I'm totally starving my GPU. There's just really not enough work to keep my GPU busy. So for those of you who are graphics aficionados, which hopefully we've got more than a few out there, it's a pretty typical problem that we have. We've got this issue where I've got, actually let's show one more thing that will demonstrate this even further. Let's go over to our API call summary. So I'm going to go to the OpenGL API call summary. It's going to show the problem even more in depth. And if I sort here by capture time, you can see that I've got set buffer address range, enabling and disabling of vertex attributes arrays, setting my vertex attribute format, setting some matrices, and drawing. So you can see all of these rows are basically these are basically all of the API calls across the entire frame. But this gives me an idea of how much each one used in terms of the capture time. And you can see here most of my time, or the large portion of my time, was spent basically setting up for a draw call and making a draw call. And you can see even these below, a lot of these were setting up for draw calls. And so you can, again, that's another hint that I'm very much API bound. I'm basically abusing the API. I've got way too many API calls for the amount of work that I'm able to submit. Now again, we've got graphics people on the line. Most of you people probably know that a great way to solve the problem when I've got lots and lots of small pieces of geometry that I'm submitting and it's really causing too much API overhead is to use instancing. So rather than submitting one draw call, changing some state, another draw call, change some state, and do that, Rather, I submit a buffer that houses all of my state changes, and then submit one draw call that's instanced, and then the GPU can actually go through that for loop effectively. And so that's what we did. We went ahead and made a modification to the application to allow us to try that, and that's what this version is. And I'll actually give you a quick overview of how that worked. So this version right here is the first version that I was just showing you. And you can see here that when I initialize my geometry, I have a vector basically of my meshes, and I go ahead and resize that. And then I have my for loop that goes through and allows me to populate each mesh box. And then I set up some of my constants for each mesh and set my translation. And then I go ahead and populate all of those full screen meshes that I use in order to do my short pass and my render pass. And then you can see also when I do the Gen G-buffer phase, you can see here that again I've got that same for loop. So I'm basically going to iterate through my vector. And again, we saw these calls. We're setting up all of our uniform matrices. We're setting up our vertex attributes. We're making all those bindless buffers resident. Then we go ahead and draw. Then we disable. Then we make resident. So we've got all of this API overhead for just simply one box basically being rendered. And that's exactly what our problem is. Our first problem is just a performance problem on the CPU. So now I'm going to close this one and show you what our new version looks like. So in our new version, you can see I'm only creating one mesh box. So now I'm not making the X by Y by Z mesh boxes. I'm only making one. I still have this for loop because I still need to set up all of the attributes for each one of my boxes, but now all I'm doing is literally just setting up those attributes. I don't have to reinitialize each mesh box, I just do it once. And then you can see here at the bottom, I go ahead and still make my single triangle mesh so that I can do those full screen. And then I'm going to go again to that G-buffer phase. And then you can see as well, instead of having that, again, that for loop, all I do is one time, I go ahead and set up my vertex attributes, make all of my buffers resident enable, and I do one call, but this time, instead of drawing, it's now draw instanced. So now I can actually submit all X by Y by Z meshes with one call. And let's see what that does to our performance. I'm going to go ahead and compile the application. And I'm going to set up the exact same analysis tracing so we can see how things look. All right, looks like we're all done. Let's go ahead and get rid of that one. Come up to Nsight, do the start performance analysis. And let's see, we're going to say System, Tools Extension, and OpenGL. I'm actually going to do one more in here. I'm actually going to do our stack tracing. So I'm going to hopefully, if everything works out well, I'm going to hopefully show you one of the other features that we have that allows you to trace from everything inside of your API tracing all the way back to your original source code. And hopefully it won't come back to bite me. All right, so we've got that set up. Now I'm going to say launch. I'm going to do the same. Actually, this time I'm going to go ahead and just start it from the beginning. Let my process run. 1, 2, 3. Hit escape. Stop my process. Now it's going to load up all of our files. All right, so already we can see some good things have happened. One is now my GPU utilization is 76%. That's awesome. That means that I'm finally able to really stress the GPU. I'm feeding it properly. My frame rate's going to go up because of that as well. Next thing I want to do is go to our module screen. This is going to allow me to make sure that all of my symbol files are loaded. It looks like my symbols are loaded, so now I'm going to be able to show you that tracing from, or the connection between the API tracing and your actual source code. Now I'm going to go back to our timeline, and you can see here, because I started at the beginning, we've got some of this startup time, but I'm going to zoom in now just to a few frames like I did before, and you can already see that things are looking a lot better here. So you can see here on the, actually let me go ahead and do my filtering as well. This is, again, this is really helpful to be able to get rid of some of these threads that I don't really care about. There we go. All right, so now we're going to drill in and we're going to see what's happening on our GPU. And you can see on our GPU now, rather than having, effectively half of the time on the GPU frame be empty, now it's probably, what, about 90% full. So it looks like I'm doing a much better job of feeding my GPU, giving it all the data it needs to be able to render a whole lot. The other thing I want to show you is, again, that tracing. That connection using the tracing. So I'm just going to choose any one of these calls. So I just simply select the call right here on the API timeline, or the timeline. Then I come back down here, and this gives us information across all the calls that are currently highlighted by this point in time. And you can see information about what the call was and everything. Then I go to my stack trace, and this shows me the stack trace. And then all I do is just double click, and this brings me right back to that exact call. So you can see it's really powerful. You can sit there and say, okay, maybe an individual call took longer than you expected. Where was that in my source code? No problem. You just highlight the call, bring up the stack trace, and double click. And then, boom, there's your memory barrier. So again, it's really helpful to be able to trace out what's happening and where you're spending all the time. Then I'll come back here and I'll show you one more time that API call summary. And you can see here now, this is exactly what I want to see. Most of the time is spent in swap buffers. That means my GPU is the one that's really spending a lot of the time, and my CPU is just simply waiting for that to be done. And obviously, we can potentially do some more offloading of things from the GPU to the CPU and so forth. But it gives you that feedback instantly of how is my balance between my CPU and my GPU. All right, so let's give a quick summary of what we talked about here in scenario 2. So again, we started our application. It had pretty poor GPU utilization, and the CPU was reasonably taxed, not incredibly taxed, but reasonably taxed. I used my application tracing and analysis features to see that the problem was I had a whole lot of overhead per draw call, and I had lots and lots of small draw calls. So all of my expense was on the CPU side, either submitting state changes or those individual draw calls. And once I just changed the application to use some instancing, and also obviously I had very poor GPU utilization. Once I changed the application to use instancing, now I can see I've got much better GPU utilization. I've reduced my CPU load. Everything is just performing a lot better. All right, let's go on and go to our next scenario. So once you figure out that you are GPU bound, naturally what you want to do is you want to say, okay, how do I improve performance on the GPU? How do I make sure how do I make things faster and faster? So first of all, what we did was obviously the screen that we showed earlier was a very, very small version, and that was by design. We have an 8-core system here. It's kind of hard to tax an 8-core system with a simple application like this. So now what I've done is I've made it so that we are more in a GPU bound situation than a CPU bound situation. So I've aided that setup. And you can see here, this is everything in its full glory. So I've got it running at, I believe it's 10 by 7. You can see all the different boxes that we're rendering. We can see all the lights that are revolving around. You can see all the transparency that you have. And again, this is all done using that deferred renderer, using those G-buffers that we talked about. And let's go see and dig in the frame debugger to see how our performance is doing there. So I'm going to say start graphics debugging. So this is different. I'm not going to use the same capabilities I used earlier. I'm going to use the graphics debugger now. And you can see here that I'm running, about 18, maybe 19 frames a second. Seems like it's jumping around a little bit, but I'm somewhere in the 18 to 19 frames a second. So that's good. It's not great, but let's see what we could do to improve that. Now I'm going to use my hotkey. I'm going to hit Control Z just like I did earlier. That's going to bring up my HUD mode. I do want to note a couple of the graphs that we've got here. In the upper left-hand corner, you've got feedback in terms of what your current frame rate is, and so that's going to give you in both frames per second and milliseconds per frame. Then also it helps you to see, if you happen to use dynamic shader editing in D3D, it'll help you to see whether or not your original shaders are being used or your substitute shaders are being used. Then the upper left, the one right below that, is a graph that gives me an idea kind of across a couple of different units in the GPU pipeline, across the geometry unit, which is going to be basically responsible for handing out geometry to the different unified shader units. The ROP unit, which is our blending unit, so that's when all the fragments come to the bottom of the pipeline and they're all blended together. And then the texture unit, that's pretty self-explanatory. And so it gives me a feel that those are not very taxed. That's not really where a lot of my overhead is being consumed. But we can see indeed on the graph below there that my GPU is very busy. Again, it's that 90% or so like we saw in our analysis session. So we can see I'm doing a pretty good job of stressing out the GPU. The other thing you have here is the batch histogram. I'm not sure why I'm not seeing my mouse, but you can see the batch histogram. And actually, let me do this. Let's change to the software cursor. Well, it's not working. There we go. There we go. Now I got my software cursor. Okay, so you can see here that I've got a batch histogram, and what this is useful for is it's useful to determine how many you typically heard the feedback that you always want to submit lots and lots of large batches, and this gives me a feel for how many primitives I have per draw call and how many draw call submissions that I have. And so you can see here that I've got basically two that have two or less primitives, two or less primitives, I'm sorry, and that one is obviously those two full screen quads that I'm doing, and then I have one that's basically less than 15 primitives. And so the other thing you can do is you can double click on these rows, and that basically enables you to disable those passes. So that can be useful so that if you happen to have either particularly small or particularly large buckets, you can instantly quickly disable just that one bucket, and you can see, okay, that character, that one, man, he totally blew his budget in terms of the number of polygons that he's rendering. Or I can figure out where I'm spending all those small draw calls, and maybe again I can use some instancing to try and reduce some of my CPU overhead. So again, that's useful on the HUD side. All right, so now let's go into capture mode. I'm going to hit spacebar on the target, on the application. And again, remember, we're doing a real-time capture here. And so the great thing is I've done a capture. You can see I've got my API inspector like I did before. But if I hit spacebar again, now my application is back running. This one obviously doesn't change a whole lot. I'm not loading new scenes, and I'm not going to new areas in a world or something like that. But you can imagine that in your application, it can be really useful for rapid iteration. So rather than the typical thing where you have to maybe save an individual frame and go off and do some performance analysis for some debugging, then figure out the problem, modify your application, come back, try it again, and just that long time between phases of doing debugging and profiling. This allows you to find those problems a lot quicker, and even with profiling capabilities, maybe even make some tuning online and actually see if those improvements make any sense, or see if those have made any improvement to your frame rate or fixed any rendering issues that you might have. So it's really great to be able to do it while your application is still running. All right, so again, we'll hit Control Z to go into our HUD mode and hit spacebar. Now the other thing is you can enter the pause mode right here from the Nsight menu. So you could just say pause and capture frame as well. So there's two different ways you can do that. All right, so I want to give you a quick overview. We really want to focus a little bit more today on profiling than frame debugging, but I do want to give you a quick overview of the frame debugger for those of you that haven't had a chance to catch Dan's talk from last week on the frame debugger. Note that those are saved. The entire presentation is up for you guys to download and listen to, or stream and listen to, so I encourage you to do that. But again, I'll give you a quick overview of some things. At the top here, we've got our scrubber. Now, if you recall, the earlier version that we had this Gen G-buffer phase was basically 95% of the frame, and then the sort and the shade was just the very end of it. And you can see here this is another benefit of doing instancing. Now we do that one submission for the Gen G-buffer, one submission for the sort, and one submission for the shade. And also note that as I'm scrubbing on the target, it scrubs on the host. So if I move this down just a little bit, you can see here as I scrub here, it's changing from event 76 to event 53 on the target, and as I do there, it's again going to do on the target and the host. So everything is completely synchronized. This is really helpful, especially if you have multiple monitors. Obviously, I'm going to have to Alt-Tab to go back to Visual Studio, but you can imagine putting Visual Studio on one monitor, put your application on another, and you can be looking over at your HUD, maybe finding a draw call of interest, and then coming into Visual Studio where you can really drill in deep into all the great information that we're giving you in Visual Studio. So that's the scrubber. Next thing we have is the API inspector. The API inspector, basically what we've done is we've given you all of the OpenGL state, and it's organized according to the GPU pipeline, kind of a virtual GPU pipeline. So you can see here we start up at the vertex specification that gives you all of your vertex attributes and your generic attributes. We go into the vertex shader, and so it gives you all of your active uniforms. If you happen to have any samplers that were active, it would have those there. Again, because we're using Bindless, we don't have any samplers. If you're using tessellation, you have tessellation control and evaluation, then geometry shaders and transform feedback if you happen to be using those. Then you have all your rasterizer settings. So this is great for all of your multi-sampling state and your culling state, and are you winding counterclockwise or clockwise and things like that. Then you have all your fragment shader state. Your pixel operations, so how do I have my depth and my stencil set up, and my stencil operations, as well as what draw buffer states that I have set up. My frame buffers, and I can look at my front and back buffers as well as my depth buffers. And then we can go through the different textures that you happen to have bound, which for some reason has me frozen just a minute. Sorry about that. All right, I think I'm going to have to restart here. I apologize for that. We'll go ahead and restart the application, get it restarted up. And I won't press that button again. All right, let's close this guy. And go back to scenario 3, begin. There we go. Sorry about that. This is highly unusual. All right, there we go. All right, so let's enter back into our frame debugger. Dan, please remind me never to hit that texture button again. Or at least have the guys look at it, make sure we can figure out what the problem is. Continuing down, then we also have the program information, which is going to show you what the link status of your program is, what the different shader types are, and what the source is. So I can select one of these, and I can instantly link right to the source for that shader, so that's really helpful. And then finally, towards the bottom, you get all of your pixel pack state and unpack state. And then you have your miscellaneous settings, and these are helpful for figuring out what extensions are supported, what GPU you're running on, what version of the driver, and things like that. So it's really, really helpful. Again, I'm not going to go super in depth on that, but just want to kind of give you a quick overview. A couple of other screens that you have are the resources page. The resources page gives you basically all of the textures and render targets that you currently have and any buffers that you currently have. So you can see here I've got a bunch of textures that are available. And these are, again, syncing them from the application that I've got running all the way over to this, onto the Nsight Visual Studio. And I can come down here and I can select one of these, and then I can go into a graphical mode so I can actually inspect that texture. I can actually zoom into the individual MIP levels and everything, so it's really helpful to make sure that if I have MIP mapping set up, it's correct, my sizes are right, my formats are right. I can also do that for my buffers, so I can come down here into my default frame buffer drawables. And one of the other cool features we have is we show you the revisions of each one of these buffers. And this is really helpful. Maybe you're doing a render to texture effect and you wanted to see where a certain draw call contributed to that texture. You can see each one of the revisions, select that revision, then go into our graphical view and zoom in and look for where the anomaly might be. So it's really, really helpful. Also note that you can run pixel history from here. Again, that's part of our debugger. I'll leave that up for Dan. The other thing you can do is from an individual buffer, you can come into our memory view. Ooh, we killed the termination to the monitor. Interesting. Okay, not quite sure what happened there. Again, I won't do that again. Okay, Visual Studio is dead again. I promise, folks, this doesn't normally happen this poorly, but anyway. All right, well, since we're running out of time, I'm going to go ahead and dive into our more profiling side of things. All right, so I start my app again, go ahead and enter my frame debugger. First thing I want to do is do our frame timings. Now, there's really two different things that we have for profiling. There's our frame timings as well as our profiler. The timings, what that does is that gives you a quick overview of what each draw call costs. And the reason why we do this is this is a super fast operation. You could have literally thousands of draw calls. Obviously, this is a very simple example, but you could have literally thousands of draw calls, and this is going to take at most a second to run. Our frame profiler, on the other hand, can take a little bit longer. If you have a scene with maybe 2,000 or 3,000 draw calls, it might take 10 or 15 seconds to run. And so if you want to do some quick back and forth just to get a quick feel for how long each draw call is taking, we encourage you to use the frame timings because that's really helpful. Up here is very similar to what we saw in our analysis. We show you kind of an overview of each draw call as it's in flight. And then down here we show you a couple of different tables with that information. So we can see here that for this one, my my draw calls, we show the draw call in three different timing mechanisms. We have basically the full pipeline cost, the empty pipeline cost, and what we call the incremental draw call cost. The full pipeline cost, basically what we're doing there is we are submitting each draw call as we would normally with the application, and then we put special markers in the command buffer so that we can find out when the draw call first enters the pipeline until the last fragment from that draw call is at the bottom of the pipeline. And so that's the full pipeline cost. It's the cost of that draw call while other draw calls are in flight. Next to it, you have the empty pipeline cost. The empty pipeline cost is useful because it kind of gives you an absolute cost for that draw call. And this one's obviously not different at all, but you can imagine that if I have a bunch of draw calls in flight, I'm going to have two things that can happen. One, for instance, I can have some some of my caches, maybe my texture cache or my L1 or L2 caches, they may actually be pre-warmed by the draw call that enters before it, and so that my next draw call might go a little bit faster. So maybe it's using the same texture, maybe it's using texels from a very similar area within that texture, and therefore it's going to those texture fetches are going to be a little bit quicker because those caches are going to be pre-warmed. Now the other thing that can happen, and the opposite thing that can happen, is that you can get back pressure from draw calls as well. So you can imagine having a very expensive draw call that has lots of geometry, maybe generates a whole lot of fragments. That's going to throw off a whole lot of threads on the shader unit, for instance, and so there's not going to be a lot of space on the shader units for other draw calls to get in. So that's going to cause them to take longer in the pipeline than they would by themselves. And so that's why we show you the full pipeline cost and the empty pipeline cost. You can look at this as, again, an absolute cost, and this is a cost given all of the other things that are happening in the pipeline. The incremental draw call cost is basically the cost of that draw call as I added it to the frame. Now you remember earlier when we were seeing all the draw calls that were happening in parallel. Well, effectively, because that first draw call in the parallel rendering took how many, a few milliseconds or a few microseconds probably. The next draw call, because the GPU pipeline wasn't full, effectively happened for free in terms of the frame time. Now obviously it took more resources, but in terms of the number of milliseconds I have in my frame, it didn't cost me anything additionally. And that's what that incremental draw call cost is. You can actually see that you have expensive draw calls that effectively hide the cost of other draw calls in the pipeline. That's kind of what those are for. And we can see here across our three phases, our first phase, remember, is our generate phase, then our sort phase, and then our shade phase. And we can see here that our generate phase is about 12.1 milliseconds, 12.2 milliseconds. We can see our sort phase is about 16.6 or so milliseconds. And we can see our shade phase is right about 23.1 milliseconds. So that's going to be important as we do our profiling to figure out. You always want to remember, when you profile, you always want to start out with a baseline and make sure your optimizations are actually helping. So that gives us a quick feel for how long those kernels are going to take. All right, so now what I'm going to do is come up here into our scrubber. I'm going to right click. I'm going to say Profile Frame. And again, this is that frame profiler. We don't have a whole lot of draw call here, so it won't take that long. But you can see it's taking a few seconds. Yeah, I'm hoping it's not a interaction with our webcast, because this was working just fine when we were doing our preparations. All right, well, let me try and restart that then. All right, yeah, it looks like some reason our application died. Let's try that one more time. All right, so we'll profile our frame. There we go. Okay, good. All right, so we profiled the frame. And now we can get a feel for where we are spending all of the time inside that GPU pipeline. So one of the new features in 3.0, and it's only implemented in OpenGL, although we're working on it for D3D for our next version, is it gives you an overview of the pipeline, and it gives you a feel for where your bottlenecks are in that pipeline. So you can see here that my shader unit was about 50% bottlenecked, maybe just under 50% bottlenecked. My L2 cache was maybe, about 25-30% bottlenecked, and my memory was about 10% bottlenecked. And we can see that even more in depth by clicking here on the bottleneck graph, and we can see here again maybe about 40% and about 10% there. And actually this screen right here was for all of the draw calls in the entire scene, and then this is for each individual draw call, so you can see that they're averaged across those. So it gives you lots of data that you can start to mine in, and you can figure out for each individual draw call, maybe draw calls within certain passes, or maybe draw calls that use certain materials, where their bottlenecks might be. And you can also do some interesting gathering of those. So I can come in here and I can say, okay, let me create a state bucket. And a state bucket is basically give me all the draw calls that have common OpenGL state. So I can say, okay, I want to give me all the draw calls that have the same fragment shader. I'm going to create buckets out of that. So you can see now I have 3 different state buckets. So now when I come back to my summary screen, I can see, okay, for that individual one, those are my bottlenecks for my shader, L2 in memory, for this draw call, and for this draw call. So you can, again, if you have, maybe you've got a Z-pass, you can make it based on those performance markers like we talked about earlier. I can make an individual bucket based on performance markers, gather all the draw calls for my Z-pass, or gather all the draw calls for my color pass or my final pass or whatever, and be able to dive in and slice up the data so I can look for where my optimization opportunities might be. All right. So the next thing we can do is we can dive in even deeper on the memory side of things. So what I'm going to do is click on here. You can see here it's got this yellow box around it when I hover over it. And now I can look in and basically see for each individual portion of the memory subsystem what the different speeds and feeds were, if you will, on the memory system. Now this card is a GTX 660, which has a published memory bandwidth of about 144.2 gigabytes per second. And we can see here that on my left-hand side, we can see that the amount of bandwidth that I used was, let's see, okay, so the amount of memory that I used here, oh, my numbers are all different. There we go, okay. We can see here that I used, about, right about 3 gigabytes of memory bandwidth. And so, that's going to be somewhere in the neighborhood of about 75%. If basically we took the amount of time that our shaders took, which is about, 50 milliseconds or so, 52 milliseconds, and figure out, based on that amount of time, how much memory bandwidth was available during that shader, we used about 75% of our available memory bandwidth. And so that's pretty hefty. I mean, it may not be a problem. We obviously have 25% remaining, but you can see I'm starting to peak in terms of my memory utilization. Then I can get a feel for how well did I utilize my L2 cache. That's right. That's why I'm doing that right. Okay. If I look at my L2 cache, I can see here that I had to serve up about 8 gigabytes of data from my L2 to my L1, but I only had to fetch, just about 3/4 of a gigabyte from my main memory subsystem. And you can see that basically that's about a 90% hit rate on my L2 cache, and that's really good. So it looks like my L2 utilization is great. That means most of my reading of those G-buffer nodes are on cache, and so that's really, really effective and really efficient. So that's good to see. But we see a slightly different story when we move up to our L1 cache. And my L1 cache, you can see that I consumed about 9 gigabytes of traffic out of the L1, but it cost me 8 gigabytes of fetches out of the L2. So that's really only about an 11% hit rate on the L1. So that's problematic. That's going to be something I want to look at in terms of optimization opportunities. So that really gives us a hint at what I want to look at for optimization. I've got on my summary screen, I can see here I'm about 40-50% shader bound. I know that my shaders are expensive. I want to see if there's any optimization opportunities there. And then in my memory, I'm really not doing a very good job of my L1 utilization. It's pretty low at 11%. That's really not significant in terms of what I want to do in terms of utilizing my memory subsystem. Now, let's go back and think about what our algorithm was for our allocation of that memory. So remember what we did was we render all of those primitives, we render all those boxes, and then for each one of those boxes is going to generate a fragment, and each one of those fragments is going to generate a node in our linked list. Now, what we do there is basically we do a dumb allocator. Effectively, we have a gigantic buffer. We have a single atomically incrementing value that gives me an index into that buffer for which structure I'm going to use. And then we go ahead and just, every single thread is going to be pounding that one allocator and basically saying, okay, give me my next node for my next fragment. And then it's going to go ahead and store that in its linked list, and then we're going to sort, and then we're going to shade. Well, as you can imagine, that's going to cause 2 problems. One, all those threads are going to be touching that same atomic value. Now, that's going to be really expensive. I mean, I've got literally thousands of threads that are all going to be waiting while one thread goes ahead and grabs the next value. Now, the other problem that's going to happen is these threads are going to come in at random times. And so as you can imagine, I've got a gigantic heap. So for the first fragment, for maybe pixel n/2, n/2, it's going to be at one location in the heap. Then the next fragment's going to come through sometime later, and so that guy's fragment or G node is going to be somewhere completely different in the heap, somewhere much later, and so on and so on. And so you can imagine I'm going to be scattering all of these different G node buffers, G node elements throughout the entire heap, and that's terrible for locality. And again, we can see that right here in Nsight. That gives us an idea of what's happening with our L1 cache. Our locality is really, really poor, and so it's going to cost us in terms of performance. So what we can do there is we can say, okay, rather than using one single allocator across all of the pixels, we want to use multiple allocators so that we get less contention, and we want to give each one of those allocators its own portion of the heap to manage so that you get much better locality, and hopefully we'll see better L1 usage with the new algorithm. And so that's exactly what we did. I'm going to go ahead and close out Visual Studio. I'm going to show you what the resulting version is. I'm going to give you a quick idea what those shaders look like. So in my Gen G-buffer, again, we're doing this all in the fragment shader. So the original one had a very, very basic allocator, and now we've got a much more complex allocator. So basically what I do is I figure out, I take my different XY location, I pass that into my allocator. My allocator figures out which tile I'm on. Then based on which tile I'm on, it goes ahead and does the atomic add for that tile. So again, that's that incrementing for my index for my next tile that's available. Then it makes sure that we're not overrunning, because obviously you may have the problem of since each tile now has a limited number of fragments that are, a limited number of nodes that are available, you could run into the problem where you overrun the number of nodes that are available. So you want to make sure that you at least have a reasonable amount of nodes that are available. Excuse me. And actually that also takes into account in the tile offset location. And so then it goes through and it goes ahead and assigns that node based on that tile offset, and then it returns it. Now the problem is when you're going through and you're allocating that node, you might run into the problem where you run over. Again, that's that allocation allocation time. And so what we did was we said, okay, let's just go ahead, since we know we can't be in this locality, we're just going to choose a random number, and we're going to just basically retry at that random bucket, that random tile. So it'll give us a quick spill algorithm that hopefully is pretty reasonable in terms of where it's going to place the additional nodes. And then you can see here, this is where we do all that population. All right, well, let's go ahead and compile this guy and see what it does to our performance. So I'm going to say Nsight, start graphics debugging. And you can see here already things are improving. I think we were around 18, maybe 19 frames a second, and already we're at 21 frames a second. So it looks like we've already had a pretty major improvement there. I'm going to enter my frame profiler. And I'm going to go ahead and profile the frame. And you can see here that already my times have improved somewhat on some of the kernels. Now remember, this one was about, if I recall, in the order of 18 or so microseconds. Let's double check that number. So it was about 12 microseconds, and now it's 22. So actually the generate phase took longer, and that kind of makes sense because now I'm not just simply doing a very dumb allocator. I've got a much more sophisticated allocation scheme, so it makes sense that that's going to be a little bit more expensive. But also note that the next two phases are much less. So now we only take 10 microseconds or milliseconds on the sort phase and 11 milliseconds on the shading phase. So already we can see we've made an improvement. So my frame rate's gone up. My amount of time that I'm spending on my sort and my shade phase has gone down, and so that's pretty significant. You can see my shader bottleneck has gone down a little bit as well. So now let's drill into our memory subsystem and get a feel for what's going on there. So we can see here that it's actually quite similar to what we saw earlier in terms of the memory bandwidth. Actually, the memory bandwidth before on the frame buffer was about 74-75%. It's now down to 53%. So that's pretty significant. Again, that's going to be the fact that we're improving our locality. Therefore, our L2 and L1 caches are going to be much better. I'm not having to fetch as many things from the main memory subsystem. Now we can see here that our L2 cache hit rate took a little bit of a hit. It's only 84% now, although we're using a lot less of that bandwidth. So it's taken a little bit of a hit, but again, we're not using it as much, so that makes sense. But the key to look at this now is look at my L1 cache hit rate. For the 6 gigabytes that I'm grabbing out of L1, I only had to request about 4.9 from L2. So now my L1 cache hit rate is about 18%. That's about a 70% increase over what I saw in the earlier versions. That's pretty significant. That's going to make a huge difference in our frame time, and you can see here I went from 18 frames a second to 21 frames a second. Well, remember what we did there with our allocation scheme. We used that random number generation, and we can see here again that my shader is still a bit of a bottleneck. So what I'm wondering is there another optimization opportunity here to see if we can make it even faster? And of course there is. I'm going to go ahead and stop that, jump to the last version, and compile that, and we'll go ahead and do a profile on that guy. So what we've done here is we've actually go ahead and enter the frame debugger. Again, Control Z and hit spacebar. and I want to show you what the new allocation scheme looks like. So in our shader file, our Gen G-buffer, now what we've done is rather than going through the, doing the random number generator, basically what we do is we just took some prime numbers, added it to our current location, and tried to go and find an entry in that bucket. And so it's much simpler. We're not having to generate random numbers and everything, but it turns out to do a pretty decent job of offsetting us so that we're not going to basically fill up us and the next one around. The other thing that happens to work out well as well is that it does tend to land in a tile that's fairly close by, and so we'll note in our profiler how that looks in terms of what our cache hit rates are. All right, so now I'm going to go into our profiler, profile that frame, see how things are going with our shaders. Unless, of course, it doesn't want to cooperate. We got to do more testing with our WebEx stuff, our GoToMeeting stuff. Let's try that one more time. I sincerely apologize for all the snafus here. All right. All right, go back to here, profile the frame. There we go. All right, so we can see here that indeed my performance has improved a little bit. So remember, my GPU time was about 21 milliseconds. It's now just under 20 milliseconds. And the interesting thing to note, these were both about 10, and now this is one that's 9, and this is about 9.8. So we've even improved what our overall shader was. And again, that makes sense because we've got slightly better locality because we're not just simply going to a random location. And one more thing, we want to drill down in here, and we can see here again we've got 5.6 gigabytes of traffic that we're taking out of L1, and we had to service that with 4.4. And that's about, trying to remember what our numbers are here, that's about a 21% L1 cache hit rate. So we've gone up even another 10% on our L1 cache hit rate. So that's really, really helpful. You can see that I've been able to use Nsight Profiler and frame timings to kind of dive in and figure out where my performance is and make those improvements to the shaders. And just want to give you a quick overview of what the overall results were. So when we first started, this was our simple shader, our simple single allocator, no tiling, no nothing. Our frame rate was 18.5 frames per second. Our overall shader time was 52 milliseconds. And then you can see there are L1, L2, and frame buffer cache hit rates in our frame buffer bandwidth utilization, 1190 and 74. Then we improved locality, but we still had a slightly complex spill algorithm. We did improve frame rates pretty significantly. We went up to 21.6 frames a second. We used about 44 milliseconds in shader time. L1 hit rates went up. L2 went down a little bit, but remember I was utilizing less of the L2, so that was good. And our frame buffer bandwidth went down. Finally, on our last one, this is again fixing our spill algorithm, make that a little bit smarter. Our frame rate went up yet again. Our shader time went up, probably mostly due to our allocation shader, or our generation shader, but then it also improved L1 cache hit rate, so obviously that resulted in improvement slightly in both the sort phase and the shade phase. So again, I want to thank everybody for coming. I appreciate you spending time with us today on the webinar. I do encourage you to go ahead and utilize NVTX in your application. You can see how helpful it was both in the frame debugger, the profiler, as well as in the analysis section to be able to give you the context of your application along with all of the powerful tools that you've got in Nsight. Again, use the analysis tracing. It gives you a good feel for what's happening in your CPU to GPU workload balance and just give you an overall view of how long things are taking. And then once you're GPU bound, go ahead and use the profiler. That's going to give you the in-depth information, no guessing, no what-ifs. Gives you exactly which unit in the GPU is your bottleneck and which one and how much utilization you've got. And I don't remember if I mentioned it earlier, but note that you don't have to be 100% of a bottleneck in order for it to be impacting your frame rate. Remember, a bottleneck is simply that's when nothing else in the GPU is able to get anything done. So even a 10-20% bottleneck can result in a pretty significant frame increase. Naturally, it's easier to go after the larger bottlenecks. If you're 50% shader bound, probably a good idea to look at your shaders and figure out where you can optimize those and tune those. And then we got a quick slide here for upcoming GTC Express webinars. But I'd like to go ahead and open the floor for any questions folks might have.
Thank you very much, Jeff, for the great presentation. And I'm going to start with some questions that were asked during the presentation. Feel free to type in your own questions as we answer these questions right now. One of the first questions I saw is, what sort of applications does Nsight support?
Great question. Nsight supports D3D9, D3D11, and we just recently added support for D3D 11.1 for those of you who are on Win 8. And also we support OpenGL. The analysis tracing actually supports any version of OpenGL, doesn't really matter. So you can do analysis tracing whether or not you're using 4.2 core or maybe some of the compatibility features. But then if you want to use the frame debugger, which includes things like the frame profiler and the shader debugger and things like that, you do want to utilize only basically 4.2 core plus some extensions. We support extensions like dynamic state access, DSA, as well as bindless graphics and some others. We actually have a complete list of those in one of the appendixes from the Nsight documentation. Also note that if your application is not compatible, if your OpenGL application is not compatible with Nsight, Nsight will actually tell you that. So it'll basically throw up a little HUD message on your application when you try and capture, so that you can say, okay, which function or which enum am I using or which extension that I'm using in OpenGL that's not compatible. And then also it'll give you hints on how you can use our compatibility log feature of Nsight to generate a log for us that you can send to devtools_support@nvidia.com. And we use those to gather data in terms of what features are most important to our users. So we encourage you to, if yours happens to not be supported, send us that log and we can use that to our database to make sure that we're going after the OpenGL features that are most important.
On that note, another question we received are, what new features are supported in version 3.2?
Great question. The biggest feature in 3.2 is the ability to, there's two things. One is we basically give you a table of all of the profiling results. So rather than putting it into graphs, we actually put it into a table right there in the GUI, as well as saving it out to a comma delimited, a CSV file. But the other great thing we've enabled is the ability to put in your own counters from the collection of GPU counters. So if when you're setting up the graphs, you can actually get a list of all the counters that are available, and also it can be exported into the config file. And so if there's a counter that is not part of our profiler that you might find particularly interesting for the analysis that you're wanting to do, you can add that to the config file, and then your counter, along with all the counters that are done for the profiler, will be in that list view that we've got. It's kind of like a little Excel spreadsheet type thing. And so that's really, really powerful to be able to go after the information that is really germane to your problem, because you have special knowledge of what's going on, and there may be counters that are available that can help you understand that better.
Another question we had was, what's the best way to go about learning Nsight? What sort of samples and examples should I be looking for to learn all the features that Nsight offers?
I think probably the best way is honestly these webinars. We obviously do lots of different talks at both GTC, especially for CUDA developers, as well as GDC, the Game Developers Conference, and SIGGRAPH. Those are all recorded and on our website, as well as, again, the GTC Express that we're doing here. But I think the other thing is we have pretty extensive documentation in terms of manuals and everything, and so you can just read through those. And we tried to write those from the perspective of a user, kind of exploring for the first time the different features of Nsight. And so it's kind of more of a user's manual than like tech documentation. So I think both of those would be helpful. And then again, if you run into problems, if you run into snags, if you have crashes like I did unfortunately during our webinar, again, that devtools_support@nvidia.com is a way to get pretty much directly to us, directly to me, and I can give you feedback and maybe help you through any problems you might have.
Feel free to post any other questions you might have in using the questions tool.
So it looks like we've got a question from Kirk asking, will the will the webinar samples be available? Yes, we will make these available. We were trying to do it after SIGGRAPH, but unfortunately we were in the throes of our 3.2 release, and that kind of dropped off the edge there. But we will definitely make these available for you guys so that you can try them out on 3.2 as it comes out. And yes, the webinar will be posted, so you know, the problem of trying to remember how to do all this stuff, you could definitely watch it, you know, a few extra times. And again, I really encourage you to look at the version that Dan did on debugging, because it goes through a lot of our debugging capabilities. Any other questions or concerns online? All right, well, the last thing I wanted to mention is we are accepting submissions for GTC 2014. Unfortunately, I think it's tomorrow is your last day. So if you have a certain area of interest, a certain area of research that you've done, and you'd like to submit a paper to GTC, the GPU Technology Conference that NVIDIA puts on every year, I encourage you to do that. You know, the abstract doesn't have to be super detailed, just kind of give us an idea what your research was and how you were able to use GPUs in order to achieve what you did. And we definitely will love to take a look at that and hopefully include you in our conference.
We have one more question, which is, do the NVTX extensions impact performance in release mode? And if so, should they be if-deffed out?
Good question. They do have a little bit of performance impact. You probably want to, you know, maybe wrap those in a macro so that it make it a little bit easier. You don't have to go through every single location, but it's not significant. I think we published numbers on that. I just unfortunately don't remember them offhand. And it is actually, another thing is it is actually something that we're constantly working on in terms of making sure those are as low impact as possible. But it's definitely not as expensive as like an output debug string or something like that. It's much less expensive than that. All right, I think that's possibly the end of our questions, and I'll hand things back over to our host.
Great, Jeff. Thank you, and thank you to Daniel too for helping with Q&A. And I think you covered actually everything I wanted to cover, which is GTC Express is an ongoing program we offer to everybody in the GPU computing community for free. So check in on gputechconf.com/GTC Express to see the forward calendar of webinars and sign up for those that are of interest to you. And as Jeff says, tomorrow is the close of our call for submissions. And just to let everybody know, GTC 13 actually attracted 3,000 people from 51 countries, featured 425 sessions across myriad tracks and topics. So it's a really terrific place for you to showcase your work. It's also a great place to come and to gain you know, one-on-one access to NVIDIA engineers and software developers like Daniel and Jeff. So if you don't feel up to submitting a proposal, do certainly consider attending. And again, in order to submit a proposal, I just go to the GTC website. The URL is right there on the screen, gputechconf.com. So thanks to everybody for joining us today. I hope you can join us next time. And with that, take care and have a great day. Bye-bye.